Where are they? Huh? I just say, if you want to start right away?
I can start right away.
Yeah.
Okay. Right. So, ladies and gentlemen, I can feel much more relaxed now than an hour ago. I'm going to talk about real things. It's, of course, a pleasure for me, for all of us here, to welcome the Nobel Prize winners for physics on 1990 in the name of our friends and colleagues, Friedman, Kendall, and Taylor. It is a long-lasting tradition of our laboratory that within what I would call the Nobel Week, the scientists which, those few scientists which don't work at CERN and get the Nobel Prize in high energy physics, they somehow, they in fact generally come back through CERN. So to give us a little bit the overview of those very beautiful lectures which are a part of of such a celebration. So today I'd like to take a few words just to introduce the speakers, perhaps to the youngest of you. And of course it's evident that presentation here is hardly needed, but I'd like to say a few words just to explain a little bit what every one of these three people have done in our field. So I'll start with Jerry Friedman. Got his PhD at Chicago in '56. He was, I think, you were a student of Enrico Fermi. And you worked with emulsions at that time. I think you also been colleague of Valent Delegdi at that time. And indeed, at that time was incredibly interesting days because the parity violation was about to come out. And if I recall well, you have been doing some work on emulsions. And with emulsion, you've proven that indeed the spin of the muon was felt by the angular distribution of the electrons, thus joining other people like Garwin and Lederman and Weyrich on this very fundamental discovery, which really changed our mind in the way in which physics was to be looked at upon, especially for parity violation. Then in '57, I think you went to Stanford and you joined Bob Hofstetter, which we celebrated a few days ago, the loss he had said as well. And then you have been working at the scattering for a number of years at Stanford, then you moved coast to coast, and you went to MIT. And you hold the Coolidge Professorship at MIT. And you are at present the chairman of the SSC Scientific Policy Committee. So now, Henry Kendall is professor since '67 MIT, and you are a truly MIT man. And you had as a professor in the thesis Martin Deutsch, which is also a remarkable person in science. And I think you did it on excited state of positronions, and then you went to join Hofstetter at Stanford. And then you were mostly responsible for the instrumentation of the last large spectrometers, which were involved in the discoveries we are going to hear about today. And I believe also today you're deeply involved in research and instrumentation. I'd like also to mention that besides worrying about science, you're worrying also about a number of things which have to do with the broader issues of the kind in which science is affecting society. So in a certain sense, I would say you're concerned scientists. And finally, let me talk about our friend Dick Taylor. He's a Canadian. By the way, Dick is the best known of us. In fact, you've been in for us because you've been working for us for a whole year at CERN, and you've been a member of the LEP Advisory Committee, and so forth and so on. You were born in Canada, and you stayed there as you're still Canadian, like I'm Italian. By the way, you are not even in a book called American Women and Men in Science. I looked for it, I couldn't find you. So maybe you should have that introduction added to this. You have, of course, played the main role in these affairs, in these experimental programs, in this discovery, as much as your two colleagues, and in fact, I would like to take this opportunity to bring in also another name into this picture, the one of Pief Panofsky. In fact, I think that Pief has been co-author of the elastic scattering paper which preceded yours, and also I think merits to be remembered because of the fantastic contribution he gave into high energy physics. We saw his contribution in the case of discover psi j indirectly, but still fundamental. We see now his contribution into the discovery of the deep inelastic scattering. Anyway, I think I will make my presentation very short by saying you welcome to CERN. Thank you for coming, to have taken the time. I know that your week has been a very long week, a very tiring week, but I think that the interest of the CERN community is very large in what you've done and what you're going to present us, and therefore I pass the microphone to, who's the first? Are you the first to speak? Okay.
Let me respond to a couple of things in Carlo's introduction. I am in the Canadian who's who. Also, you might like to know that Pief Panofsky was invited to Stockholm by the Nobel Foundation and the Academy, and even to dinner at the Palace. And Pief's comment was they've made up a new category. It's called Godfather, because this is the third time that someone from Pief's lab has gone to Stockholm. So what Carlo says is exactly right. Pief is deeply in this, as was Jim Bjorkane. Well, it's nice to see so many people here. I came by about 2 o'clock. They were already lining up. Let me say how pleasant it is to be back in familiar surroundings, and how truly pleasant it is to be back in these particular surroundings talking about something else. I will use the word luminosity only once today, and that was it. Henry and Jerry and I have divided up the task of describing the experiment for the Nobel Lectures in a roughly chronological fashion. And it fell to me to describe the early days, the construction of the apparatus, and a bit of the history, including the initial proposals for the scattering experiments and the early elastic results, because they, in some real sense, preceded. Now, my talk today will be, I hope, quite a bit shorter and lighter than the one in Stockholm, since so many of you are already expert in the field of deep inelastic lepton scattering. So all I should have to do is explain to you what an electron is, and then I can go home. Also with this audience, I have no need to explain that the number of people involved in these experiments was quite a bit bigger than 3. The 3 of us owe a great debt of gratitude to many people, particularly the ones that built the 2-mile accelerator, led by Pief Panofsky and Dick Neal. That accelerator was really one of the great technical achievements of the 60s, and gave us a really golden opportunity to pursue the experiments which were recognized this year up north. Another group to whom we owe a great deal are the colleagues who helped us build the experimental facilities, and I've made a list here. This is certainly not a complete list of the people who were involved. Where have I got? Oh, this thing? Away we go. Yeah, and he isn't even a theorist. I wrote down just the names of physicists because I thought probably only the physicists would be familiar here, except for perhaps Dirk Neat, who worked on a lot of things at Stanford and who I think would prefer to be called an engineer. I have color-coded these. The ones in green are the ones, green and red, are the ones who were on the first inelastic experiments, and the ones in black were on other experiments around us, but we were building the apparatus in common. And so Henry will have lists of people that cover. These are the ones that were involved only up to the time we started the experiments. Okay. Well, in the lecture that I gave in Stockholm, I tried to make the point, which I will just say here and not try to convince you of, that a lot of the advances in our knowledge are really coupled to improvements in the accelerator technology and in the building of experimental apparatus. I also tried to point out a little bit less directly, perhaps, that it's important that the accelerators and the apparatus be built to high quality standards. And I don't want to talk much about that at CERN because that would really be preaching to the choir, because this is still the place that I think does that more than anybody else. So I'll go back now to when things started. The study of proton structure using electron scattering began very soon after the commissioning of the first half of the Mark III accelerator at Stanford, the first traveling wave linear accelerator. And it had an energy of about 225 MeV, much more current than the circular accelerators that were around at that time. And Bob Hofstadter and his group built a sort of quasi-permanent piece of apparatus for electron scattering experiments, which consisted of a 180-degree magnet with 18-inch radius. And you can see that rotated around the target so that you could change the angle, and by changing the excitation in the magnet, change the energy, and get spectra of the scattering of electrons from various targets. The first evidence that I can find for hydrogen is from 1953, and this is a polyethylene target, and you can see just a little tiny bump here, which is the hydrogen in the polyethylene. The carbon with Z squared working for you is much bigger. And so shortly after this, they built a gas target, because that really isn't good enough. They built a gas target, and with the gas target, they discovered that the scattering was greater than the Mott scattering, which was an issue in those days. They actually says we have to be sure that the magnetic moment scatters electrons. It's amazing in how short a time something like that becomes gospel. Whereas, I mean, to us it's absolutely automatic that that would happen, but in those days they hadn't seen it, so they pointed out that they wanted to actually see it. On the other hand, it was not as much scattering as you would get if you had the full scattering from the anomalous moment, and from that they deduced a size for the proton. The size was about 7 × 10⁻14 centimeters, and that was the first time anybody had said that the proton was not a point. Now, in the same, this was now about 1955, about 2 years after that first curve was taken, and in that year, the accelerator, the facilities at the end of the accelerator were completed, and so you now had 550 MeV and growing. And Hofstadter and his group had built a spectrometer, also mounted on an old Navy gun mount, so it could be rotated. Now 36 inches in radius of curvature, and therefore able to go up to 500 MeV. And so he could repeat the experiments. They also built a liquid target, which made quite a bit of difference. You can see now the elastic peak from hydrogen is pretty clean and pretty much all by itself, and you can make excellent measurements of the amount of cross-section in there. And this is one of the fairly early curves showing the proton with a form factor that's far from constant, falling down, checking that essentially the form factor is only a function of q squared, which it is in the one photon approximation. It has to be, but it doesn't have to be a one photon exchange. So you're checking all those things, and in the particular model that they picked, the radius was 8 times 10 to the minus 14 centimeters. And I think from that time on, people were looking for structure in the proton, because once somebody tells you that something has a size, then after that you have a feeling, at least, I don't think it's logically necessary, but you have the feeling that if it's got a size, there must be something inside that you can take apart and have a look at. Now, it was about this time that the experiments generated a desire for higher energy, and it was again Bob Hofstadter who suggested an accelerator which was essentially which had 1,000 klystrons, and each klystron fed 10 feet of accelerator, so that was 10,000 feet, which is just about 2 miles, and that's where the 2-mile accelerator came from. And it began in 1956. There was a first proposal in 57, and construction started in about 1962. And so some years later, but just to give you some impression of what we were talking about, some years later the accelerator existed in the hills behind Stanford University. This is the 2 miles, whoops, my tummy all lit up. Starting at this end, down to here is the 2 miles, and then this is the experimental area that I'll talk more about in a minute. This is 2 miles of accelerator. The accelerator is buried 8 meters underground, and the building you see is the building that houses the klystrons that power the machine. Now, we never did put 1,000 klystrons in because they were too expensive. They stopped at 250 and said we'll put the other 750 in later. We never did. They stayed expensive. Now, when I got there, one of the things which was not finished was the design of the experimental areas, and after a lot of fooling around, we ended up with 2 areas, one for electrons and gamma rays and the other things that these strange people from Stanford were interested in, and the other one for good old hadrons, with a target room here, which could be heavily shielded, and you could take hadron beams out of that into 2 areas. Something is feeding back. I hope I'm not doing it. Okay, so now we're down at the end of the accelerator, and just to give you some weak impression of what's going on, this is end station A, and this is end station B. This is the hadrons, this is the electrons. And poor old Bob Mosley put his streamer chamber out beside end station A because he thought there'd be lots of beam time available out there. Within about a year, he moved it over into the central beam to get away from us. Well, I'm now going to start to talk a little bit about the machinery that we built to fill up that big concrete building that we had there. The simplest, the experiment is still the simplest one that you can do. You detect only one electron coming out of the interaction with a huge beam going by this way. You don't try to detect the recoil particles, you just detect the single particle going in this direction. And most of the design of the instruments you can get from this very simple equation of the secondary energy of an electron scattered from a mass m at angle theta. You can from this calculate the resolution that you need in angle when you have to, how well you have to know the angle to make sure you're still seeing elastic, and you can calculate the maximum energy that you need at any given angle. That turns out to fall rather fast with angle, so that by the time you're out to, I think it's 17 degrees, the energy is already half the initial energy, and the spectrometer doesn't have to be so big. Well, I said I was going to keep it light. This is a picture of Panofsky's blackboard after an afternoon's talk once in about early 1964. And you can see us looking at various areas. I mean, there's a spectrometer here that has a maximum momentum of 8 GeV, and another one in the forward direction, which would only go out to 20 degrees, which would go up to 20 GeV, the maximum energy from the accelerator. And you can see various designs here. Here's one where the electrons are simply bent up, and you have a series of otoscopes to measure the orbits in that spectrometer. This looks suspiciously like one of the DAISY spectrometers that were already, if not already in operation, very close to it, but it has a whole bunch of otoscopes all the way through it too. This may be I think this is part of what was called the twisted quad. The trouble was that with spectrometers that turned up in the air, the 20 GeV spectrometer got either very high, it had to go way up in the air, or it had to go way down in the ground, and that was technically a little nasty, and it took a long time to fix that. Well, we went on with these things. You can see down this side, this is, I think, probably Henry's writing, isn't it? Yeah, it looks like Henry's writing, and this is about how we're going to tell the difference between an electron and a pion when we're making measurements. Well, it wasn't very long before one of the two spectrometers was in pretty solid shape. This is a picture of the so-called 8 GeV spectrometer, because it goes up to 8 GeV. It has 2 bending magnets and 3 quadrupoles. Nothing could be simpler. Sits at the target here, rotates about the target on rails, and the focusing is in the next slide. The focusing is point to point in the vertical, so that you can disperse the momentum, and line to point in the horizontal, so that you can, so that the angles are correlated with position horizontally, and you can measure the angle. So here is the vertical orbits, and you can see them. Things that have different angles coming from the target end up at the same point if they have the same energy. Different energies end up at different points. So you're dispersing an energy. In the horizontal plane, you can see the particles that all come out with the same initial angle end up at the same place in the detector, at the detector plane. And let's see, these are different angles, and particles with the same, with different energies are not really affected very much in the optics. So up in the top of that thing, you have to have some counters, and the counters that are laid out horizontally will measure theta for you. The ones that are laid out vertically will measure p. So you measure theta and p, and then all of this stuff is designed to select out electrons from whatever else is there. Now, as I said, the 20 GeV was a much more difficult machine to build, because we couldn't figure out how to go up, we couldn't figure out how to go down, and Panofsky and Coward proposed a machine in which the bends were horizontal, and you used some quadrupoles to twist the beams around so that you could still get p and theta orthogonal. And it was much too complicated, and I didn't like it at all, but it was hard to stop, right? I mean, it's like stopping somebody you know, and it was not easy. And so finally I had to appeal to higher authority, and Carl Brown calculated that the third order aberrations in that particular spectrometer were terrible. And at that point I was able to kill it, and about a week later Bert and Carl Brown came up with a fairly clever idea, which was simply, when you get halfway through, to put in a crossover and turn it over so that you came back parallel to the ground again. The ground is down here somewhere. And so this thing did not go up forever. And the only thing that was wrong with it was that you had to add some sextupoles, because without the sextupoles the focal plane was lying almost flat, and you had to get that up to some reasonable place so that real counters could be built for it. So the 20 GeV spectrometer, this is an artist's conception way back in the days before they were built, consists of all these magnets that you just saw, the bending magnets and the quadrupoles and sextupoles in this S shape, and then a big shield up here, detector sitting inside, and the target back here. And of course there's a big distance between the target and the first magnet, because this is the device that has to go down to very small angles, and so you want it to be a big distance so that you can get close to the, when you get close to the beam pipe, the angle is a minimum. Well, I said in Stockholm that I really was sorry that I didn't have the kind of oratorical skill that was needed to recreate the 3 years that it took us to go from these paper things to the design, from the design to the actual instruments. And looking back, it's remarkable. I mean, we were still arguing about the 20 GeV spectrometer in the fall of 1964, and the instruments were finished about Christmas of 1966. We did physics with them in early '67, and if I looked at something comparable today, even though these are fairly simple devices, I don't think there's a chance. I mean, you wouldn't be through the environmental impact report in that time, let alone have them built. So there were a lot of problems. We had trouble getting the precision magnets. We had to make those gigantic frames to hold the magnets. They had to hold the magnets so they stayed in line as you rotated them around. The rails had to be laid in the floor to very high tolerances. And all these problems were attacked by a really marvelous group of mechanical engineers and technicians. Because of the way the laws are in the United States, you have to hire professional union people to install such things. And we did that, but the engineers were even able to infect these hardened union people with the enthusiasm. And I lived for most of a year in real fear that a union steward was going to come in without telling us, and he'd find a millwright building a wooden scaffold while the carpenter was running the crane. Now, Dave Coward, when we had a little mini celebration at SLAC, found some old slides, and I want to give you some impression. They do give some impression of the way the work was being done. This slide was taken on the 10th of December in 1966. And you can see here that there are 2 quadrupoles mounted in this big frame. There's not much else going on here. One of the big bending magnets is over here. This is where we tested the magnets. There was the power supply was over in a building over here. The cables came out of the pit. So this was the test stand. So this represents the status of things on the 10th. And the next slide is the 12th. And on the 12th, you can see that 2 magnets have been mounted. The third magnet is, the last magnet for the 8 GeV is over here in the test stand being measured. You can see the coil sticking out of it, so it's really already being measured, and other pieces are being put in. Other magnets are being brought in for the 20 GeV. So this gives you, I mean, this is 2 days apart, right? And that gives you some idea of the speed with which things are moving. And here is the 24th of January, a couple of weeks later, with Christmas in between, and the spectrometer is, it's backwards. The spectrometer is all set up, ready. It's set at 0 degrees, ready to do the mapping of the aperture using the beam as a probe. And that was, I'll just show this very quickly. Oh, God. This is the result of that. You can see this is what we computed, the black line, and these are the measurements made with, and it's about 3 or 4% different. And we used what we measured, not what we calculated. Well, it wasn't very long after that spectrometers themselves were pretty well complete. You can see all 3 of them here. This is the 8 GeV. They're not showing up very well. It's probably still too much light in here. This is the 8 GeV spectrometer, all ready to run. This is the 20 over here. You can't see much, but you can see one of the magnets up there. And this is the 1.6, which is the farthest back. We don't have a target yet. We don't have all our monitoring in, but we're getting started. So about this time, we were writing proposals. Proposals had 3 parts: elastic scattering, comparison of EP and electron and positron cross-section. That's just a test of 1 photon. And since it was all right, it never gets talked about again. And a survey of inelastic scattering. And I put that in because it shows that we weren't really that clear about what we wanted to do. Well, we had to build a target. We first built a target which was very simple, had a reservoir and essentially a can that you could pressurize in thermal contact with the reservoir so that hydrogen would condense in here if you put some gas in under pressure. And the idea was that convection would carry away the heat from the beam. That was wrong. We had to build one much more complicated in which the hydrogen circulated, and I won't bother going into that at all today. We needed monitors. It was very simple. We had a Faraday cup, which was big enough to stop the electrons, and we measured the current. We had a toroid, which in those days was almost new, and there was a lot of expensive engineering to read it. The only thing that was really a little bit novel about the design, I think, was the online computer. The online computer actually controlled the magnets, read the monitors, read the data as it came in, and could be used to produce online cross-sections. It wasn't the first one to do this, but it was one of the large ones that was, and one of the first ones that did both control and read-in, and we had a lot of fun with it. Well, now I'm going to switch over to sort of nostalgia. This is Panofsky and me. Well, you may not recognize me. I'm the skinny one, and that's my wife hiding behind Peef there. This is in the counting house just as we were getting ready for the very first runs of the spectrometer. This is another prettier view, it's backwards, of the same room with Hobie DeStabler and Les Cottrell down here trying to get ready for the first run. This is the output from the computer is going to come up on this scope, and these are various controls for beams and things like that. It's, I mean, you have to be very finely calibrated to tell that this was somewhat ahead of its time at the time. There's Hobie DeStabler actually lining up the beam. That shield sits out there over the television cameras that look at various screens. This is Henry Kendall practicing his bow to the king in 1967. There was an enormous amount of electronics. I mean, now that much electronics would take up about that much space, but in those days it was quite a bit. And Henry spent a good deal of time bent over like that. Well, all of this happened, all of those pictures I think were taken within a very short time of each other, and this was when the experiment was coming together. And I guess all of you had a moment like that when LEP came on last year, but for us it happened when we started to put everything together and measure our first elastic cross-sections. We were looking into places where nobody'd looked before, and like the days at LEP, we had the biggest and the most expensive machine up to that time, opening up space where nobody had ever been. Hundreds of man-years are focused down into trying to make everything work. And often you have nasty difficulties at times like that, and it takes you forever to get on, and by the time you do, you're so tired you don't care. But we were very lucky, and everything went fairly smoothly. And when the target was full of hydrogen, the computer started to put events on the screen, and within a few minutes we had an elastic peak. I must stop very soon. There's the elastic peak. Henry took a picture of me with the elastic peak at that time. Henry took the pictures. There aren't any pictures of Jerry because Henry and Jerry tended to anti-commute, and Henry took the pictures. So that is that. I won't show that. You can take that picture, or the other one, which is better, this one. Take that picture and project it in missing mass. This is P and theta, so you can find the missing mass, and when you do that, you make a one-dimensional plot, and you get back one of the old peaks like you used to get in the good old days. And I'm sorry, that thing's got. You get a nice, clean, elastic peak with its almost perfect radiative tail. It's sitting a little high in mass, but you can fix that. And unfortunately, What happened in this particular case was that the data lay right on the curve that had been postulated for data that was up in here. I mean, right up in there, they had found this curve. And all the years in between when people had made measurements, there was one thing where life changed a little bit, and that was when Cornell came into the game. Up until that time, people had used F1 and F2, the Dirac proton plus some extra anomalous magnetic moment. And when Cornell, which included Professor Schopper, I think, did the experiments, that's the thing that prodded everybody over to the G's, where you had an electric moment and a magnetic moment. Okay, I just have a couple more pictures. These are three people that had quite a bit to do with what we did and what I did in particular. This is Mosley, who was my thesis advisor. This one you probably can recognize. It's Bert Richter, and it's Pief in the front. And I think I'd better stop. This is 1963. That shows I can put Pief on a pedestal, and I'm still taller than he is. And well, finally, all of this leads to, well, there's one more person that had quite an influence. That's the two of us before. This won't be very interesting except to some half the audience that know both of us. This is before we were married in about 1949. And it all ended up here at Stanford on that particular 9/90/10/17. Thank you very much. Yeah, I can't see. There we go.
Thank you. Let me start again, as Dick did, with our collaborators. This was a reasonably good-sized group by the standards of that time, but is of course no longer a big group. But these are the names of the physicists that were on any of the papers that were reported from the whole inelastic program. I've made only one spelling mistake. Marty Breidenbach is spelled EI there. What I'd like to do in this segment of the three talks is spend about a third of the time to give you some sense of the theoretical and experimental situation that described hadron structure and hadron interactions at the time we moved into the inelastic scattering measurements, and then spend the rest of the time that allotted to me to discuss the actual inelastic measurements and the first series of discoveries that we made, and then roll it over to Jerry Friedman to carry through the discussion to what was really the end, which was the final identification of partons, which we discovered in the middle of the program, and which were really identified as such by Feynman, with the identification of them with quarks. This was not one of a series of measurements where something sort of came up very quickly, unexpectedly, the way it did with Richter and Ting and the J psi, where at least at the Stanford end of things, at 3 a.m. they were beginning to take some data, and by 5 or 6 a.m. there had been a discovery made, and by 7 a.m. the bottles of champagne were opening. This was really a very slow roll, you might say, experimental information came in which was new and puzzling, and then it was digested slowly, and then what finally happened was a very interesting interplay between experiments and theoretical developments which were stimulated by them, and in fact this took a number of years to work out before the whole picture became clear. It was really at least something of order 4 years before there was general agreement on what it was that had been found in the program. So there was no moment of sudden revelation in any sense. It sort of leaked out like some drum leaking away, and the liquid just sort of drains down. So the first part of this is what I will call the 1968 hadron. In the late 1950s and early 60s was the great accumulation of information from proton machines and secondary pion beams. The dozens of hadrons and hadronic resonances that were identified in that period, and it's dozens and dozens that were accumulated. There was a good deal of pi and proton hadron scattering, and it was all what you would describe as soft. The energies of the machines were, of course, nothing like they are today, and the results, the angular distributions, were characterized by momentum distributions which went as high powers of the momentum, exponentially in e to the minus something times t. And the consequences of all of that was that the hadrons themselves were believed to be soft and not have any point-like substructure. And that persisted for quite a long while, and the theories that were developed largely reflected that information from the experimental program. Now, of course, the large number of hadrons was initially in what you could best describe as a bewildering array. And it was in 1961 that Gell-Mann and Neyman came through with the first very powerful classification scheme, SU3. Gell-Mann was wonderful for naming things. That was the eightfold way. A couple of years later, in 1964, Gell-Mann and independently George Zweig, who was here at the time, discovered that they could generate this whole eightfold way with combinations of three basic things, which were really not thought of really as particles at the time. The origin of the name itself is somewhat interesting, and there's been some mythology connected with it, and I've tried to get it sorted out. The word quark, spelled that way, is used in Finnegan's novel. Pardon me?
Finnegan's Wake.
Finnegan's Wake, Joyce's novel, Finnegan's Wake. What apparently happened, according to Murray, is that he invented a sound which he wanted to apply to these, which if you spelled it would be Q-U-O-R-K. And then he ran across this word in Finnegan's Wake and decided to appropriate this word, but the original pronunciation. And those have sort of stuck together that way, so it is usually pronounced quark. In any event, they had spin a half, and in the most economical way of describing this, they had fractional charges, although that was not an absolute necessity. The generation of the eightfold way with quarks was quite successful, and from that came the picture of the nucleon with three of what we now call valence quarks. This success and stimulation by Murray and others initiated a whole series of measurements looking for quarks somewhere or other. There were subsequently studies looking in cosmic rays, in accelerator-produced beams, and what you might call oil drop searches looking for fractional charges from quarks that might have accumulated somewhere in matter, just kicking around. And none of those was ever successful at the time or since, and it has long since been decided, and now there's a consistent picture as to why these things are not seen. Here's just a quickie slide to show you some of the scattering results. The momentum squared here and GeV squared does not go to a very high value. Pi minus p scattering, pi plus p scattering, and just coasting off with no discernible structure and no rise later as one sees now. And again, another one a piece of one of the multiplets from the SU3 classification at the time, and some of the quark assignments in terms of down, strange, and up. Now, so the picture that emerged then was this simple one, which is now very familiar, but in which the quarks were not identified as physical objects. Gell-Mann, at least himself, made pains to make sure that people understood that these were basically, in some sense, the word was used, mathematical devices as generators from those groups, and not actually a constituent. The predominant way of describing all of this came to be known as came out of S-matrix theory, along with what was pretty quickly called the bootstrap theory. It got launched in about 1960 or so. The stimulus for this being that calculations with strong forces simply led to intractable problems which never were solved, and in particular perturbation theory was just completely unjustified and wouldn't work. The bootstrap idea, which became the most widely accepted approach to understanding the strong interactions, said that there were no fundamental particles. It got the name nuclear democracy, that each was a composite of every other one. The interactions were dealt with by trying to decide the structure of the S-matrix, which gave the amplitudes for scattering between all possible kinds of states. And there was a search for self-consistent solutions for this array of amplitudes. A number of different approaches to this developed, and I haven't even tried to list them all here, but two that come back in, and that three rather, that Jerry Friedman will talk about a little bit later, were Reggie theory, which was developed far enough to apply to the relativistic S-matrix, and it had some fairly substantial successes in that it dealt fairly well with the regularities of the hadron resonances, and it still provides a satisfactory explanation for the large energy but low momentum transfer, so-called soft scattering, which was all it had at the time. Well, this gave rise to some other pictures of it, which Jerry will talk about. The last one that I'll list here is vector meson dominant, and that had some relevance to electron scattering, because it was an attempt to deal with the with electromagnetic interactions with the hadrons. And essentially what it said was that a photon could materialize into one or another of the low mass vector mesons. Once you had this going, then the interaction between these vector mesons and the hadrons could be dealt with by what was already known from the other strong interaction theories. And because this was pretty successful in some of the real photon physics, two things came out of it. First, many people believed that it would succeed with the virtual gammas, which we would be using in the inelastic electron scattering. And second, it implied that since this was already believed to be known from the hadron scattering, that the inelastic electron studies would not show anything. And this sort of hint was what led people, as we now see, led people astray for some long period. There was no reason to believe anything else, but it set the scene for the, for example, the design of some of the experimental equipment that we were building. There are two other matters that I'd like to touch on. One was the development of current algebra. Again, Gell-Mann had his hand in right at the origin of that. It became quite important by 1966, and a number of people, a good number of theorists were working on it. The important part of there are two things that are important about it. First, it started with the idea of free, non-interacting quark field, and so in some sense it had quark physics built into it. And when people later started developing things with the current algebra, hidden inside it was its origins in the quark theory. But again, Gell-Mann pointed out he was not suggesting that these things he was working with were constituted constituents of the hadrons. One thing that came out of the current algebra was what you could sort of call an industry of sum rules. This is one of the pieces of the original current algebra work which has persisted. It was apparently wonderfully done, and it stood the test of time. Adler did the first of them, and then there were a number of other people connected with it. Scaling, I'm going to pass over for the moment and come back and talk about in a little more detail later. The other piece was the proposal that in fact the quarks were real and constituted a physical hardpoint constituent in the hadrons. This had an awful lot of trouble in the period before the experiments. And it's convenient in talking about it now to distinguish constituent quarks from what you might call the mathematical quarks, which formed a satisfactory basis for the classification schemes. In trying to reconstruct this and talking to a lot of theorists in the last a month and a half or so, the center of gravity seems to have been that the bulk of the theoretical community simply didn't like the idea. The reasons were fourfold. First was the failure to produce these things, and in a sense it was unprecedented, because anything that you really expected to have as part of your understanding, you could make under some circumstances or other. Now, the quarks that were used to construct the hadron resonances needed some kind of heavy binding in order to produce the resonances, and that was that gave you trouble if you wanted to have them as sort of independent devices in there. Thirdly, they were spin-a-half, and the hadron ground states in many cases had symmetric wave functions, and there was a problem with the exclusion principle. And of course there was the matter of the fractional charges. Now, you could contrive ways to circumvent all these problems, but it was really substantially awkward, and on the whole people did not accept it. But not all of them fell into that category. A number of people persisted and continued to do calculations. It was a kind of phenomenology, and it was pretty successful for low energy processes and for hadron characteristics. I've only been, only been able to find one published paper that dealt with the constituent quark model and actually went into high momentum transfer lepton scattering. Gottfried did one calculation and came out, as one does with this, with point particle cross sections, very large. But he, in his paper, was very skeptical that that would in fact prove true when it was tested against the data. There's some other information that Jerry Friedman will touch on later, and Bjork Kane's studies of this. Here are a couple of quotes from Murray Gell-Mann that will give you some idea of how he felt about it at the time. And he made clear also that whether or not they were real, they certainly formed an enormously satisfactory basis for understanding the classification schemes and would never be abandoned just because they weren't found. In talking to him recently, and looking back at some of the statements he made, for example, the Berkeley Conference in 1966, he largely indicated that he didn't believe them, and that was sort of the common understanding at the time, but he reserved sort of 4% of what he said for the possibility that they might be there. He did not reject it. Other people were considerably stronger in their rejection of it, and one can go back through the literature and find substantial quotes that people say the thing is just the constituent quark idea is bizarre and, as you see here, ill-founded. Well, that was where things stood when we were designing the experimental program and the equipment. Here's the basic diagram for the inelastic scattering. Now there are two independent variables, the energy loss, nu E minus E prime, and the momentum transfer. In none of the experiments we did we look for the final hadronic state. The accelerator there is pulsed. It were very narrow pulses, 360 cycle repetition rate, and the experimental area would simply fill up with neutrons during this blast, and you couldn't do coincidence experiments satisfactorily. So that's the equipment in schematic form. A little bit of the scattering formalism. I don't need all the details of this for the talk, but a couple of things are important. The general form of the differential scattering cross-section is here. One divides out the point scattering, which is well understood from quantum electrodynamics, and the information on the target system in inelastic scattering is buried in two functions, W2 and W1. So far as one can tell, initially independent functions of the independent variables nu and q squared, and there's a tangent square to the angle there. And one measurement of this cross-section has contributions from W1 and W2. They're not immediately separated, and you have to do some juggling, some programming, plotting these as a function of angle, scheduling experiments carefully in order to separate these. I note that for later discussion that there is a unique relationship between the momentum transfer and the energy loss, which is applicable solely to elastic scattering. The q and q squared and nu are connected for elastic scattering, but not for inelastic. And then again, to get a jump on some of the later discussion, another formulation of this, which I haven't time to go into, in terms of virtual transverse and longitudinal photons, this ratio turned out to be important, but it was not something that we measured in the first round. One of the daunting experimental difficulties that we had to deal with, and was very well known before the program started, was the question of radiation of real photons during the scattering event. In a space of final energy, electron energy E prime, initial energy E going out here, the elastic scattering kinematics lie along a curve, schematically something like that, and various resonances would be on parallel curves. This would be the threshold. Here is a typical threshold for pion production. And if you wish to measure a cross-section deep in the spectrum, inelastic spectrum down here at E and E prime, the consequences of radiating photons either after the scattering or before the scattering means that the whole triangular region in here can feed this point with electrons which are not what you want to measure, and can corrupt your measurements. And you have to, in order to apply appropriate radiative corrections to data taken at that point, you need the completely corrected cross sections over the entire triangular region here. This was a twofold problem. One, it taxed the computers substantially of the day, and second, the theoretical expressions for these deep inelastic radiative processes were not known with an enormous amount of confidence, and we had to feel our way into it. Jerry Friedman and I independently had some years before worked on these problems and had done some experimental measurements, and in fact had looked at triangles of this sort and had convinced ourselves that it was intrinsically a tractable problem. But it still took quite a bit of time in the experiment and represented one of the biggest problems. The computer that we had in the experimental complex was one of the larger ones of the day. Les Cottrell, one of the senior scientific programmers on the experiment, gave a talk a few weeks ago at Stanford and mentioned that computer technology had improved a great deal over the years, and that a computer of the size we then had is now only found in washing machines. Very quickly, these are typical triangles. We would take data all sitting at a one constant angle, take spectra thusly, and then by interpolation techniques fill the entire space with interpolated data, and then let rip with the correction program. I'm not going to go into it any more than that because we did successfully solve them. But this is what the spectra would look like. Here's 10 GeV in 6 degrees. There's an elastic scattering peak there in red, a scale change of a factor of 7 there, and this is the elastic computed radiative tail. This is an inelastic spectra, and you see the first 3 resonances in the proton, and it's sitting on a large diffuse background with a relatively structureless background. After the corrections, subtracting out the elastic contribution and making the other corrections, you get this, and this is the ratio of the two, and you see the corrections amount to 30 or 40% of the observed cross sections at some places. They change sign in an irregular way, and they have to be fairly well known if you wish to hold the ultimate uncertainty in your measurements at the 1% level. So it was not really trivial. Here's how a few typical spectra might look. Quite fine-grained in the region of the resonances. Corrections have been made here. The elastic peaks are gone. At low momentum transfer, you see prominent resonances and not much of an inelastic formless distribution there. At intermediate momentum transfers, the resonances are beginning to disappear, and what you're seeing are finite size effects there and a much bigger inelastic distribution. And finally, the resonances are just gone, and that's what's left. Well, I won't go into that anymore, and I will show you the first discovery that we made. This is some segments of the inelastic distributions at a missing mass of 2, 3, and 3.5 GeV, and there are the two higher missing mass distributions. And two things of that were totally and completely unexpected to us. One is the fact that they were very large, and second, they showed relatively no momentum transfer dependence. And here again is the curve that Dick Taylor showed for elastic scattering. The finite size effect is enormous. And what that's telling you right away, without any further analysis, is that you're scattering from something which has no discernible size within the framework of that particular set of measurements. So there is point-like scattering. That was a surprise. This is what was in our experimental proposal for scattering of, I think it was 17 GeV electrons at 6 degrees, and this is what we observed. Between 1 and 2 orders of magnitude discrepancy. So that was certainly a big surprise, and it was new, and it was the first hint that there was something going on down inside. The second thing has come to be called scaling, and it was predicted by Jim Bjorkane on the basis of current algebra expectations, and it's gotten to be known as Bjorkane scaling, and the limit in which it's satisfied is called the Bjorkane limit. Energy loss and momentum transfer getting very large with this ratio held constant. Then his prediction was that those two structure form factors I indicated, nominally dependent on two independent variables, would become dependent on the single variable omega. Now later it's become convenient to use the reciprocal of that, which is commonly now x, and in what I'll show you later, and what Jerry will show you, we use x and omega somewhat interchangeably. I'll come to the other questions of the quark stuff a little bit later. But what happened was that I happened to be doing the data analysis at the time we first began to accumulate some of this, and this shows you what happens if you just plot the information and nesting a number of the spectra as a function of energy loss. And you see that it's just more or less scatters around here. The resonances show no particular nesting. And if you took a spectra over a wider range of parameters, well, you could fill this whole region down here with data. But BJ leaned over my shoulder and said, well, why don't you take a look at that as a function of the scaling variable? There was still the unknown ratio R, which at that time had not been measured. It had a rather comfortable range. It could be anywhere between 0 and infinity. And so we worked it out both for R equals 0 and R equal infinity, and there was this spectacular nesting of the data. And this was the discovery of scaling. This is essentially the first plot where it was seen. And I must say that I wondered at the time how Balmer must have felt when he laid the data on the hydrogen spectra and the wavelengths into that formula that he conceived, and just saw everything just fit so beautifully. And it certainly was clear to me that there was something going on here, and that was shared by my colleagues as soon as they saw it. As time went on, the range of the measurements improved, and we were able to carry out the separations of W1 and W2, now F1 and F2, and this shows a very large range of data, all nesting rather beautifully here for both F1 and F2. So that's scaling worked out in more detail. Now, this set of measurements was finished in the spring or late spring of 1968, and in that summer in August, Dick Feynman came up to Stanford and sat down with us. Jerry Friedman and I were both there, and had the scaling and the Q-squared independent results in front of him, and he went off to a motel one night and he came back with a parton theory, which for the first time naturally explains scaling in terms of a rather simple mechanical model. And this is now, in a sense, legend, and it's what he came up with. He did not make the identification with quarks, and in fact, a number of people who started calculating with the parton model did not make that connection either. There were calculations by Drell, assuming that these things were protons and mesons. But the picture he came up with, parton simply means part, that's where the word came from, was a scattering off one of these constituents and struck as if it were free. And this assumed the impulse approximation and means that the high momentum transfers occur not to some correlation of constituents in there, but quasi-free particles. I mentioned that we did these separations of F1 and F2 just to show you the scheduling of the data taking that enabled us to carry that out. These are 75 sets of matched points where there were different angles selected at similar values of q squared and x that we used. I'm not going to go in more detail in that, but it required a good deal of scheduling of the data taking to do those separations. With Feynman in the act, so to speak, there was immediate attention to his ideas and the interest in what was considered to be the importance of these measurements went up very high. And so now other theorists began to come in with very interesting results. Two of them is all I will take time to discuss today. The first was that this quantity R, the ratio of longitudinal to transverse virtual photon cross-section, was predicted by the vector dominance model. The second was that Carlo and Gross showed that in the framework of this parton model that there was a relationship between the structure functions that could illuminate the question of what the spin of the parton was. And in particular, if this ratio was 1, then you had spin-a-half objects, and if the ratio was 0, namely not having any magnetic moment, you got spin 0. The first of those predictions, the question of vector meson dominance, looked like this. These were the first measurements of R for the proton. That's where the measurements lay. This is schematically where the vector meson dominance would have it go. It went up without limit there, and that was the end of vector dominance as it applied to the substructure of the nucleon. Then, as far as the spin of the parton was concerned, and now you see one is closing in on the quark interpretation, although not yet there. The red line is the spin-a-half prediction. The bottom here at 0 is a spin 0 prediction, and there's no question about that either. Well, I will leave this with a picture of Feynman in his first public discussion of the parton theory at Stanford in the fall of 1968, with his enormous enthusiasm, laying out this picture, which ultimately became controlling. And I will let Jerry Friedman carry you through to the end. Thank you.